A black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. The event horizon is very simply and a bit hand-wavingly, but it's a reasonable description. It's just, if you can imagine a sphere in space, and if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape. So the event horizon separates the interior of the black hole from the external universe. We'll see a bit later why that's a bit of a hand-wavy description. But another description of the event horizon, which confused people all the way through the history of black hole research, actually, certainly to the early papers in the 1930s and perhaps even post-war, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. And that's a direct prediction of Einstein's theory of relativity from the external perspective. If you watched, for example, an astronaut falling in towards a black hole, then from your external perspective, you'd see their time pass more slowly, slower and slower and slower, as the astronaut approached the black hole, until on the horizon you would see their time stop. That suggested to many people in the early days that a star couldn't collapse to form a black hole. It confused them. They thought, well, if a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial early conceptual problems, which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole. So time passes at 1 second per second on the watch of an astronaut falling in, but from the external perspective, time freezes on the horizon. So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole? Now, in pure, just in Einstein's general theory of relativity, actually, it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not, and is still not, understood.